moment. Okay, yeah, let's do it. So in this case, we're given two integers. They're called n and m. Well, this sounds kind of familiar. Find position of the rightmost pair of equal bits in their binary representations. This is almost exactly the same as the previous one, except instead of looking for the place where they're different, we're looking for the place where they're the same. So in this case, we want to assume that they're going to be different, up to a certain point where they're going to be the same. And at that point, we're going to say, oh, okay, return that, or return 2 to the power of wherever that index is going to be. Okay, so how should we do this one? I'm thinking probably pretty similar to how we did the last one. Now, we did the last one using like a recursive formula, and we found it was pretty neat. It's kind of cool. Well, we also found that in the last one we were able to use kind of a math trick, which made the problem a little easier, a little more interesting. And then we used some bitwise operators, and we found, you know, what can you not accomplish using bitwise operators? Anyway, at this point, I don't know, should we start with a recursive function like the last one? I might not go through it in as much detail. Maybe hey, if you're up to the challenge, maybe what we can do is dive right into the one-liner and try to make the recursive function right here. What do you think? Is that going to work? Let's try it. We'll see how it goes. So basically, the general structure is that we're going to put our function in here, and we're going to call that function and put the result in here. You know, it's just like normally we would say, like, call this function f with an input of 5, for example, right? So we're going to put our arguments in there, but the function itself is going to be something in parentheses because we're going to be basically declaring it. We're going to define what that function is inside these parentheses. That's the idea. Okay, so this is a function. It's gonna, what's it gonna do? Well, should we put in n and m or like a and b or something like that? Let's try maybe no. Yeah, let's try maybe no. Let's do this thing b, okay? It's gonna represent a binary number. And basically, b is the thing that's gonna be like kind of our position, right? It's gonna start as 1, and then it's going to be 1, 0, then it's going to be 1, 0, 0, then it's going to be 1, 0, 0, 0, 0. Or I might have put one too many zeros in there. Anyway, the point is, it's going to be the thing that we're going to use to compare. Hey, I've got a word for this. I'm pretty sure this is accurate. I believe that this is called a mask. Okay, so this is going to be our mask. It's just going to move. It's going to be a 1-bit mask. Normally they have more than that, or sometimes I should say. And it's just going to move from the right to the left. It's going to start in the rightmost position, and then it's just going to go 1 to the left, 1 to the left, 1 to the left, until it doesn't need to anymore, basically. Okay, so what do we want to be comparing here? Well, we want to say is n and, let me put these in parentheses. So is n and b going to be equal to, well, hey, is it going to be equal to m and b? Are they equal? That's what our ternary is asking. That's what I love about these ternary operations here. Wait, did you say that right? Ternary operate? Is that what it's called? Anyway, our comparator, right? We're using a ternary. It's kind of like it's actually asking the question, you know? It's like, is this? And then we'll put, yeah, if it is, if it's not. So if they are equal, what do we want to do? Well, basically, we want to return b. It's the thing, you know, it's the thing we're looking for. We found it, right? This is the bit where they're equal. If it's not, if they're not equal here, then we say, oh, okay, well, you know, try again. Return whatever you would get by calling this function with the same mask, the same b value, but now left shifted by 1. Try that. And we want to start this off with a b value of 1. So that's why we're going to put that in as the argument here, as the input, because it's basically going to be the initial value of b. So my claim is that this is maybe one way we could do it. Let's try running this. We'll see what happens. Yeah, it's a way we could do it. Hey, you know what? Just for fun, just to sort of spice this up in a way that's maybe going to be different from the way we've done it before, we could do something like this. You might be looking at that and thinking, whoa, hey, is that okay? Well, basically what I'm saying is, we're either going to, like, each of these things is either going to be 0 and 1, or 0 or 1, right? Like, this is going to be 0 or 1, this is going to be 0 or 1. We want to know, are they the same or are they not the same? That's basically it. So if we want to compare these things, then we could just subtract them, right? If they're the same and we subtract them, then we're going to get a 0. If they're not the same and we subtract them, then we're going to get a 1. Now we're looking for where they're going to be the same, right? We're trying to find where they end up being equal. So we're trying to find where would this thing be 0. So since we're trying to find where this thing would be 0, we actually want to flip this around. So we want to say, okay, this, put the b over there. So is that better? I would say in some ways, yes, because it's shorter, and in other more important ways, no, because it's less clear how it's working. There are two issues here. Number one, this doesn't produce a Boolean. It produces like a 1 or a 0, right? So it's producing, or technically a -1, but the point is, this is producing a number, and we're just relying on the fact that 0 would be typecast to false in order to make this, a proper condition for our ternary. The other issue I have with it is the negative, the minus here, is not really communicating what we want it to, because it's not really showing us that we're actually trying to compare that they're equal, right? That's not implied when the reader looks at this. And so in order to make this more clear to the reader, we probably should do it this way. I think it's worth it to have those extra characters. I mean, look, if you really need to economize some bytes here, you could take off one of these. It doesn't need to be both, but it's probably better that it is. Just, I think it's good to get in the habit of using the triple. Okay, so did that pass all the hiddens? I can't remember. Yeah, okay, so we've tried it now, and it is passing the hiddens. And hey, look at this. 100% complete the corner zeros and ones. Ooh, what do we get? Oh, yeah. Okay, so I have to say, after going through 8 of these challenges where we only get 100 each, that was a bit frustrating. Anyway, but this I think they've atoned for it. The 4,000, that feels good. That's like an extra 500 for each of those things, 500 monies. So okay, cool. Nice. Let's continue. Actually, wait, not continue. Let's close this thing because we want to do some other stuff to this. And hey, look, I'm on a page of my own again. That's funny. Anyway, okay, going back to this, we want a different way of doing this. This is a cool way of doing it. I think it's neat that we're able to just sort of whip out this recursive function like it's no big deal. And that's one of the really nice things about JavaScript. It's nice and flexible. It's quite forgiving. It'll let you do what you want to do most of the time, and that's kind of a nice thing about it. Let's put a 1 on that one so it doesn't end up running it, and we'll just clear this because we want to think of a different way that we can handle it. Now, in the previous one, in task, what was that, 23? Yeah, so in 23, we ended up using math. We used the power of math to sort this out, to actually get an idea of how we could do this. Basically, we subtracted the numbers because we found in the previous case, well, actually, hold on a sec. Let's just go over the whiteboard for a sec, and I'm going to switch colors. Let's grab the pen. Okay, so let's say we were looking at, I don't remember the actual ones from last time, but I think it was something like this, and then like a 0, 0, 1, 1, 1. Yeah, I think that was it. It's 23 and 7. And we found that in that case, when we subtracted these things, it basically gave us what we were looking for, because we'd get a 0 here, we'd get a 0 here, we'd get a 0 in all the spots where they're going to be equal, and then we'll get a 1, maybe some other stuff to the left of it, maybe not, but we would get a 1 in this place where they actually differ. So a negative, a minus, that definitely helped us for that one. Now in this case, we're looking for an example where they're different, and then equal, right? As opposed to this one where they're equal, then different. So let's try that. Let's see. 1, 1, 0, 1, 1, 0, I guess. And then what do we want to do? 1, 1, 1, 1, 0, 0. How's that? Is that okay? Should we make this also a 0? Yeah, let's make that also a 0 so that they actually differ. Yeah, that's cool. I appreciate that. So This would not work quite the same if we were to do a minus, because we'd have like a 1 minus 0, 1 minus 0, then a 0 minus 1. We might get different results here. What we want is something like this that would give us the same result if the numbers are of the same kind of type. Like over here, we were looking, if the numbers are the same as each other, we want something that gives the same result. If the numbers are different from each other, we want something that gives that, that result for this one anyway. Now for these, hey, we can think of a way that would actually make these produce the same thing. It's not that different from this. Instead of subtracting them, let's add them. Because look, if these are different, well, there's only one way for them to be different. One of them's a 0, one of them's a 1. There's no way around that. When we add a 0 and a 1, we're going to get a 1. We're going to get a 1, we're going to get a 1, and we're going to get a 1. But over here, if we try to add 1 and 1, well, that makes 2, right? So that means we put a 0 here, we'd carry the 1 over there, we'd get another 2 over here, so we'd carry the 1 over here, and we'd get a 1 there. So what were we actually looking for in this one? Well, it was this. Right? We're trying to find the bit where they're actually equal. So technically what we want actually is kind of like the opposite of this, right? We want like 1, 0, 0, 0, 0 instead of 0, 1, 1, 1, 1. And also we want to kind of ignore all the rest of the junk to the left of it. So I don't know. Is there some way we can do that and just get the least significant one? If only we had a way. I don't know. Oh yeah, this. Okay, so we'll use that. But first we need to get here. So let's take stock of what we have over here. This is n. This is m. This is n plus m. And then what we would have over here is the opposite of it. So it would be not n plus m. And then we want to do this to it. Okay, we can do that. So, did everyone get all this? Anyone have any questions about it? I can leave it on screen for just a little while longer if you want. Up to you. But the main thing is that that's sort of going to be our game plan. And the reason I'm asking right now is because we are going to switch screens in just a sec and go back to the code window. So hopefully all this is good, making sense. Yeah, let's go back. So basically, we're going to add the two numbers. We're going to do a not, a bitwise not. So where was that? Bitwise not, yeah, this over here, okay? So it's just switching all the bits. We're gonna use a bitwise not, and then we're gonna take the result of that and put it into this trick over here, just like we did with the last one. So let's try that. We're gonna do n plus m. We're gonna put a big old tilde out in front. And then, since we want the least significant bit of this, we'll do an and with the negative version of that. Let's try running that. What do we get? We got the right answer. Great. Okay, well, not too bad. All right. Is this the best way to leave it? I don't know. We could probably modify it in some other ways. I mean, what we did find is that negative not something is going to be the same as that thing plus 1. I'm pretty sure that's something that we found. So maybe we'll make a modification like that. I don't know. We could try it right now. N plus m plus 1. Unless I'm doing this wrong. Let's find out. No, that would work. So it's up to you, whichever you prefer. I'll probably just switch it back to what we had before just because, bitwise operators, right? Okay, so let's go back to the beginning here. Let's make that a 2. And I think our math strategy is working here. It seems like we got all the right answers, so that's pretty good. But again, just in the spirit of the corner of zeros and ones, we want to make this as bitwise as possible. So I have something kind of neat. If we go over here, we found that in this last one, yes, we were able to use the minus, but we were also able to use an XOR. And we found that that worked because it basically showed us like where they're the same and where they're not the same, right? So XOR basically says, hey, if you're the same, you're getting a 0. If you're different, you're getting a 1. Well, couldn't we use the same thing over here? Couldn't we use pretty much the exact same thing over here? Because we're basically saying, hey, if you're different, you're getting a 1. If you're the same, you get a 0. Well, that would produce, at least up to this point, which is the point that matters, it would produce the same thing. So maybe that's better. Let's try it. We'll try doing the same exact thing. In fact, yeah, we'll just keep it the same. We'll do this. So a little bitwise operator in there. And still works. Okay, so that's pretty not bad. Again, we can do what we did before and say, instead of repeating ourselves with n XOR m, n XOR m, we can say n XOR equals m. And now we just need n on its own over here, which means we don't really need the parentheses. And so that's pretty nice. And again, this is the same as just doing n plus 1. So we could do it this way. It's up to you. I guess I'll just leave it like that. I think that's pretty decent. Yeah. And I think it's kind of interesting how we were able to use almost the exact same strategies for this one and the previous one. I guess, there is some symmetry to the two problems in terms of what they're asking, but in particular, I thought it was cool that we were able to use XOR in both cases, and then just put a not on this one. It sort of makes sense. Anyway, that's going to be it for this one, I think. We've got 3 different ways of doing it. So using our recursive function, using a math operation, or using bitwise operators, strictly bitwise. Well, okay, I guess it isn't strictly bitwise because it's got the plus, but we found there was a way to do it with just bitwise. So anyway, the point is, which of these is the best, which is, better? I don't really know because, I'm looking at these and I'm thinking, well, yeah, these are just strict operations, right? These are like built-ins, no problem. But I don't actually know what's going on behind the scenes, like when you say do an XOR or something like that. So I'm looking at this and I'm thinking, well, yeah, that's good because, that's not as good because it's got to run a bunch of times, right? It's repeating this function. The call stack is getting bigger and bigger. I guess that in and of itself is a reason to maybe doubt this one. But number one, I don't think it's going to be a huge issue. Like, these numbers aren't going to get that big. At most, it's going to execute 30 times. So I don't think we need to worry in this particular case. And also, like I was saying, when we do an XOR, I don't know if that's like how long that's going to take, how the performance is going to differ between the two. Not really sure. So you'd have to ask an expert on that one. But as for now, I'd say we're probably done with this. Nice job, everyone. I'm happy with what we've produced here. So yeah, let's get the heck out of here. And hey, look at this. We're free from the shackles of the corner of zeros and ones.